Okay, first of all, let me thank all the organizers for inviting me, giving me the opportunity of talking a bit about my research. So the things that I will say will belong to two works. One is joint with Carlo Pagano, and the other one is joint with Alina Ostafe and Umberto Zani. Okay, so let's say the general framework of my talk belongs to the setting of arithmetic dynamics, which I know not too many people are familiar with, so I just want to give a little bit of context. So this is a subject that started to be studying systematically towards the end of the 1980s. And what it does essentially is it studies the arithmetic properties of dynamical systems that have this form. So you pick some algebraic variety X over a field K, you take a rational map F from X to itself, and then certain arithmetic questions arise when the base field has an arithmetic interest. So for example, a global field or a local field or a finite field. So what do I mean by arithmetic questions that arise? I want to just give a very brief example, which I think explains this issue very well. So let me say that from now on, I will denote by Fn, this way the nth iterate of a map F and not the derivative. Okay, so for example, one typical dynamical object that people studied, even in like classical dynamics, is the set of preperiodic points of a map. So a point, in this case, a point lying on the variety is called preperiodic for the map F if the orbit of P under the map F is fine. And there is a theorem of Narcot from 1950, which tells the following thing. So if you have a number field K and the morphism of the projective space to itself of a degree at least 2, and then you look at the set of rational preperiodic points, then this is a finite set. So this is a prototypical example of an arithmetic dynamics result, because on one side we have a quantity which is purely dynamical, namely the set of preperiodic points. And on the other hand, we have a property which is of a very arithmetic flavor, right? The finiteness of a set of points. And in fact, like the finiteness of this set of rational preperiodic points follows from the more general fact that the set of all preperiodic points, not just the rational ones, is a set of bounded height. And this is really a typical Diophantine statement, right? So this is a clear example of what's going on. So now, one of the reasons why number theory started being interested in arithmetic dynamics is the fact that there are some analogies between certain results in arithmetic dynamics and certain other very well-known results and constructions in the theory of elliptic curves and Abelian varieties. And one instance of these analogies is the one between Tate module of elliptic curves on one hand and their Galois representations, and what are called arboreal Galois representations on the dynamical side. And this is what I'm most interested in, and I'm gonna explain very briefly the construction. The construction is the following. So you have, you start with your favorite field K and pick a point in K, and then you look at a rational map from the projective line to itself of certain degree D, and then you have to assume this hypothesis, which essentially says that in the fibers over alpha of the iterates of F, there are no ramification points for F. And once you do that, and then you look at the set of all preimages of alpha under all iterates of F, then, which is of course a subset of the algebraic closure of K, then this set has a natural structure of infinite regular tree. And so here in the slide, you can see an example in degree 2. So this is for a map of degree 2. How does this construction work? So you start by putting a root of the tree and label it by your base point alpha. Then you will have two descendants from alpha that are the solutions of f of x equals alpha, namely they are just the points of the fiber over alpha. Then at distance 2 from the root, you will have solutions of f square of f equals alpha, and so on and so forth, right? So this will be an infinite tree, of course, and here you just see the first 3 levels of it. So what does it mean to be connected by an edge in this tree? It simply means that f maps the point that lies below to the point that lies above. Because if you think about it for a moment, then you see that tautologically, of course, f maps the fiber of fn plus 1 to the fiber of fn, right? So you have this natural way of connecting nodes. Now, the key observation is that once you take the absolute Galois group of your base field K, then this will act with its natural Galois action on the infinite tree. And it does so via automorphisms, namely the action of every element of the absolute Galois group gives an automorphism of the tree. So an automorphism of the tree is just a bijection of the set of nodes, which preserves connected nodes, right? Preserves the relation of being connected. And in doing so, this action induces a continuous homomorphism from the absolute Galois group of the field to the group of all automorphisms of the tree. So these are two profinite groups. So in particular, they're topological groups. Of course, the absolute Galois group has its natural profinite topology. And the automorphism group of the tree is also a profinite group because you can view it as an inverse limit of the group of automorphisms of the first n levels of the tree, and then make n vary. So you get these continuous homomorphism, and this is what is called the arboreal Galois representations attached to F with base point alpha. So this is not really much of an exotic object. In fact, like if you think for a moment and you know the construction of the Tate module of an elliptic curve, then the Galois representation on the Tate module of an elliptic curve is the arboreal representation attached to a specific dynamical system, which is that where the variety is the elliptic curve and the map is multiplication by p. So in a way, this is a wild generalization of this concept. And of course, in doing so, we are losing a lot of structure because in the case of elliptic curves, we have a Galois group acting on a finite dimensional vector space, while here we just get a continuous homomorphisms of profinite groups. Anyway, the image of such representation is, of course, isomorphic to the inverse limit of the Galois groups of the splitting fields of Fn minus alpha. And this latter object, of course, is well defined even without any hypothesis on ramifications on the fibers of alpha. We just look at all the Galois groups and take the inverse limit. And this is the object that is called dynamical Galois group of the pair F alpha, right? And really the study of these dynamical Galois groups is really a matter of interest in modern arithmetic dynamics. Yeah, let me just mention that, of course, in studying dynamical Galois groups, we are only interested in isomorphism classes. So we will look at pairs up to this equivalence relation. So we'll say the two pairs are conjugated if we can transform one into the other by a Möbius transformation with the rational coefficients. But okay, I mean, this is not, it's not even too relevant. So now, once we have these arboreal representations, or more in general, dynamical Galois groups, we can certainly wonder how big their image is. And of course, on the elliptic curve side, you have the very well-known open image theorem of Serre, which tells you that Galois representation on the p-adic Tate module has infinite index image, if and only if E has complex multiplication, which just means that the curve has a lot of endomorphisms, many more than normal. And so this theorem falls in a general philosophy according to which whenever you have a representation of this kind, then if the target object has many symmetries, then the image of the representation has to be small. And in the dynamic setting is much less clear what it means to have extra symmetries. But certainly one specific condition that forces the image to be small is the following one. So we say that a rational map from P1 to itself is post-critically finite, and we just abbreviate by PCF, whenever the orbit of all the critical points is finite. And critical points are just ramification points for the map. So when people do arithmetic dynamics, they call them critical points, while algebraic geometers call them ramification points, but they're really the same thing. Okay, so and here what we have is that for a generic map, say when the base field is a global field, the index of these representations is in general expected to be finite. But for post-critically finite maps, one can actually prove that the index is infinite, so the image is really small. And of course, you can naturally wonder when the image is abelian, right? And here, again, on the classical side, you have a very well-known theorem of complex multiplication, which tells you that when you look at the Galois representation on the Tate module of an elliptic curve, then the image is abelian exactly when E has complex multiplication. And this also has to be defined over the base field, but you can also remove this condition, and then the image will be virtually abelian, so not very far from being abelian. But anyway, so again, we have this phenomenon where like a specific property of the image, that of being abelian, is implied by the existence of extra symmetries. So in analogy with these, we expect also dynamical Galois groups, abelian dynamical Galois groups, to only occur in presence of extra symmetries. But as I was saying, this is much harder to formalize. And in fact, at least for polynomials, it has only been done at the beginning of last year by Andrews and Patch. And the conjecture is the following. So whenever you have a polynomial over a number field and some base point alpha, then the arboreal representation associated to this pair has abelian image if and only if the pair F alpha is conjugated to one of the following. So either the map F is a power map and the base point is a root of unity, or the map is a Chebyshev polynomial, which you can evaluate in either x or minus x, and the base point is the sum of a root of unity and its complex conjugate. So this conjecture falls, of course, again, inside the same philosophy. It tells us that not only in order for the image to be abelian, we need post-critically finite maps, and definitely power maps and Chebyshev polynomials are post-critically finite. But in this case, it forces an even stronger condition, because these maps, they actually come from endomorphisms of algebraic groups. So they definitely can be sort of thought as extra symmetric. So what I want to do in the remaining time of my talk is to like give partial results towards this conjecture. And the nice thing is that there are sort of completely disjoint symmetries towards strategies towards attacking this problem. And so the first of all I want to briefly talk about is what the same authors of the conjecture proved in their paper. And so they focus on the say easiest non-trivial case, which is that of quadratic polynomials with coefficients over Q. And they also assume a stability condition. So they also assume an additional hypothesis on the pair, which I'm not gonna explain here. But anyway, so suppose you have some quadratic polynomial over Q, which you can always assume it to be of the form x squared plus c up to conjugation. And now there are only three different post-critically finite polynomials of this form, which are x squared minus 1, and x squared minus 2. So the first step of their strategy is to prove that if the image is abelian, if the dynamical Galois group is abelian, then the polynomial needs to be post-critically finite. but they do so assuming this extra hypothesis of stability. So we'll see later that you can prove these without any additional hypothesis. But nevertheless, so the first step is to reduce to the post-critically finite case. And here, so x squared is the power map, and x squared minus 2 is the Chebyshev polynomial of degree 2. So the difficult thing is showing that if f is the map x squared minus 1, then no matter how you choose the base point, you're never going to get an abelian dynamical Galois. And now I don't want to get into details of how this is proven, but I want to talk about the baby case, which is the case of f equals x squared. So in this case, the conjecture tells us that the dynamical Galois group is abelian precisely when alpha is a root of unity. Okay, so I just want to show you how can one actually prove that alpha needs to be a root of unity. Of course, this case is so easy that you can prove it in several different ways, but I just want to talk, say, about the general strategy, because then it's same that goes on in the difficult case. So suppose that this Galois group is abelian, and which is equivalent to say, of course, that the whole tree is contained in the abelian closure of your base field K, which is Q. Sorry, I don't know why I wrote K, but I meant Q, of course. So, and we want to show that alpha is necessarily a root of unity. And so the idea here is very simple. So whenever you have a point in the tree, so this point will be mapped to alpha by some iteration of the map F. So we'll have that Fn of gamma is alpha. And therefore the height, the usual logarithmic height of gamma is 1 over 2 to the n of the height of alpha. This happens because the height of gamma squared is twice the height of gamma. Okay, so what happens is that if you pick a sequence of points into inside your tree with the property that each of them is mapped to the previous one by f, and the sequence starts with alpha, then the height of gamma n has to tend to 0 for n that tends to infinity. But now there is a very nice theorem of Amoroso and Zanier, which tells you the following thing. It tells you, look, that if you have a number field and you take any point, any algebraic number in its abelian closure, then the height of this number is bounded below by a positive constant, unless the point that you chose is, of course, 0 or a root of unity, because in that case, the height is 0, right? So even if this abelian extension is infinite, the height of its elements is bounded below by a positive constant. But now you can easily see how this goes, right? So now we have a sequence of points whose height tend to 0, and all of these points are abelian, and therefore they must all be roots of unity. But if they're all roots of unity, of course, also alpha is a root of unity, because it's just the image of this gamma n, right? And the case of x squared minus 2, so the Chebyshev polynomial, is completely analogous. And the hard case, so the case x squared minus 1, it has a very similar spirit, but it uses much more sophisticated tools. One of them is the called Silverman canonical height, which is a kind of height attached to a specific rational map. And on the other hand, so you need sort of another constant other than Amoroso-Zanier constant, and this is going to be the constant given by the Arakelov-Zhang pairing of two polynomials, which is like a very technical object. But the spirit of the proof is again the same. So you show that there is inside, if the representation is abelian, then there is a sequence of points that whose height tend to the wrong thing in a way. Okay, but the sort of while Andrews and Peschel were working on the problem, I was working on the same problem independently with Carlo Pagano, so we didn't know of each other's work, and we sort of naturally assumed a completely different approach, which is more like group theoretical somehow. And that goes as follows. So whenever you have a degree 2 map, and you look at the automorphism group of the tree, which I'm gonna denote by omega infinity, this is a very special group because it's a pro-2 group, so it's an inverse limit of finite 2 groups. And so elements in this group can be uniquely described by what is called the portrait of an element. So this is a sequence of 2 to the n tuples. So first entry is just a digit. The second entry is a pair of digits. Then the third entry is like given by 4 digits, and so on and so forth, where all of these digits are 0 or 1. So they belong to F2. So what, how does one see an element of this automorphism group in this way? Digits just tell you whether you have to swap a pair of broader nodes or not. So if we go back for a second at the picture of the 3. So for example, having a 1 as a first digit means that you have to swap the 2 halves of the 3. Right? While if you have a 0, it means that the 2 halves of the 3 stay still, you're not moving them. And then digits on higher levels tell you what you have to do with pairs of adjacent nodes at every level, whether you have to swap them or not. This is why there are only 2 digits, because only 2 operations are possible. Okay. And okay, so all elements can be described in this way. And now for every n, there is a continuous surjective homomorphism from omega infinity to F2, which is just given by summing the digits at level n, right? So here I'm using F2 to denote the cyclic group on 2 elements. I'm not interested in the multiplicative structure. So for every n, you get these continuous homomorphism phi n. And this homomorphism also generates the space of characters of the group. But anyway. Now what's interesting is that the commutator subgroup of this omega infinity is the intersection of all these kernels. So the commutators are exactly the elements such that the sum of the digits at level n is 0 for every n. And the quotient map from omega infinity to the Abelianization, to the quotient with respect to the commutator subgroup, gives an isomorphism with an infinite product of F2. Okay, so this is in particular a vector space over F2. And what we could prove is this very innocent looking lemma. I'm lying a little bit about it because there is an extra hypothesis, but it's not relevant then in what goes on, which tells you the following thing. It tells you, look, whenever you have 2 elements in the automorphism group of the 3 that commute, then when you look at their images inside this big F2 vector space, then you have to find 2 vectors that are linearly dependent. And therefore, what happens is that whenever you have an abelian subgroup of this automorphism group of the 3, then whenever you look at its image modulo commutators, then you're going to get a subspace that is at most 1-dimensional. And this is a very, very strict constraint, of course. But now we need to translate this condition into a dynamical condition, because we are dealing with here, this is just valid for all subgroups of the automorphism group of 3, but of course we are interested in subgroups that arise as dynamical Galois groups. And for doing that, let me just give this easy definition. So whenever you have a quadratic polynomial of this form, then the adjusted critical orbit is just the orbit of 0, where the first point has the opposite sign. So you're gonna swap the sign of the first element of the sequence, but essentially it's just the orbit of 0. And so the lemma that provides the link with the dynamics of the polynomial is the following one. It tells you, look, if your critical orbit contains no 0, then the dynamical Galois group of the polynomial with the base point 0 is contained in the kernel of the map phi n precisely when Cn is a square in K. Okay, so this sort of gives the link between the two. And if you combine everything that I said, you get this theorem which is part of this joint work with Carlo Pagano, which says, look, whenever your dynamical Galois group is abelian, then the post-critical orbit generates a subspace of k square of k star modulo squares, which is an F2 vector space that is at most one-dimensional. Okay, so this really translates the condition of being abelian into like an arithmetic condition. And this holds really for any base field K. Here, I'm not, until here, the fact that K is a number field does not play any role. But if in addition, you assume that K is a global field of characteristic not 2, then F needs to be post-critically finite. So this also works in positive characteristics. And this is essentially an application of Falting's theorem on points on curves of high genus. So again, when you focus on the case where the base field is Q, then you get that, of course, here I formulated everything with base point 0, but you can just put any base point and you essentially nothing changes. You just have to change the critical orbit by translating it by alpha, but the theorem is really the same. So whenever the base field is Q, again, we get that if the Galois group, if the dynamical Galois group is abelian, F needs to be post-critically finite. So one of the three polynomials that I was talking about. And this is really without any stability assumption over F. And then one can combine this with certain results of Anderson, Hamlin, Poonen, and Walton, together with local class field theory, to show that for the tough case, which is x squared minus 1, when the dynamical Galois group is abelian, then all odd p-adic valuations of alpha and alpha plus 1 must be 0. And this reduces the problem to checking a finite number of cases, which we did, and therefore we could prove that the conjecture holds true for quadratic polynomials over Q. And we are currently extending these to actually quadratic fields and unicritical polynomials, which are essentially polynomials of the form x to the n plus c instead of x squared plus c. And last, I want to talk a little bit about this other work that is joint work with Alina Ostafè and Umberto Zanier, that sort of came out of a parallel project. And the result is the following. And again, it uses completely different techniques. So because this is essentially just a height argument. And a first result is the following. So whenever you have any rational function, so here we're not restricting to polynomials. So here any rational function is good, and any coefficient field, any number field is good. If the dynamical Galois group is abelian, then the map needs to be post-critically finite, right? But this really uses the fact that we are working over a number field because it's a ramification slash height argument. And now this can be combined with a pre-existing result of Alina Ostafè, which is based on ideas of Vornicich and Zanier, which uses some unlikely intersection results. And the result is the following. So whenever you have a rational function over a number field, and the degree of the numerator is strictly bigger than the degree of the denominator plus 1, then there are only finitely many elements in the cyclotomic closure of K that are mapped to alpha for some n. And this happens unless your map is conjugated to a power map or a Chebyshev polynomial. So this condition on the degree of the numerator and degree of the denominator, it means essentially that infinity is a fixed super attractive points. And this is really sort of necessary in the argument, because the fact that it's super attractive means that it's super attractive at every Archimedean and non-Archimedean place, and this really gives you certain height bounds that then are crucial in the proof. So okay, so if you combine the two results above, you get that whenever you have a rational function of any degree, but with coefficients over Q, and this is not conjugated to a power map or a Chebyshev polynomial, and the dynamical Galois group is abelian, then the map needs to be post-critically finite, and all of its critical points need to be strictly preperiodic. So strictly preperiodic means that the orbit is finite and it never comes back to the critical point. So these critical points cannot be periodic. And of course, polynomials always have a periodic critical points, which is infinity. And therefore, in particular, Andrews and Patch's conjecture holds true for all polynomials over Q of any degree, okay? And let me just briefly conclude by saying that if you want to try to generalize the conjecture to rational maps instead of Galois groups, then you cannot expect it to be true without modifications. And this happens because there are counterexamples, which again, they naturally come from endomorphisms of algebraic groups, which in this case are elliptic curves. And these counterexamples are given by lattice maps. So for example, here in the slide, I just wrote down one example. So you have these elliptic curves over Q of I. You take multiplication by 1 plus I on E. So the vertical maps in this diagram are just the x coordinates, and the map phi is the map that makes this diagram commute. And then one can show easily that the dynamical Galois group of this map is abelian, while phi is not conjugated to a polynomial because these lattice maps are never conjugated to a polynomial. For example, because they never have a periodic critical point. And it is actually possible to characterize all lattice maps that give rise to abelian or virtually abelian dynamical Galois groups. And hence I concluded my talk.